Okay, let's start with example 14.2 just to get warmed up. Here we have a 1750 kilogram car going down the incline. It's going down a 10-degree inclined road at a speed of 6 meters per second. So there's mass information, we have an angle information, we've got velocity information. If the driver jams on the brakes, causing his wheels to lock, okay, determine how far S, okay, so we're looking for S, something that's the displacement, how far the tires skid on the road, okay. Coefficient of kinetic friction between the wheels and the road is mu k. So there is all the kind of information, type of information that we have. So look at this very important statement. Now, how are you going to solve this? Well, you could actually solve it using chapter 13, force and acceleration. We'll see that in a minute. But we'll see that because we've got essentially force information, right? There's forces here. We've got mass. There's a friction. Okay, we'll do that in a minute. Because we've got force information, velocity, and displacement in this problem, we can use the principle of work and energy. Okay, so I want to remind you, okay, force, velocity, and displacement. That will allow us to bypass this equation. We'll see that in a minute. Okay, so the first thing, like always, we draw a free body diagram. And there's our car. We have weight going straight down. We've got the normal force, and we've got a friction force. Okay? As this car is skidding until it comes to rest, we've got these three forces. Okay? So I want to just jump to the end. This is where we're going. We want to use this equation, the principle of work and energy. Initial kinetic energy plus the sum of all the work done on the particle is equal to the final kinetic energy. Okay, so what is our initial kinetic energy at state 1? Okay, it's half mv squared. Half times, there's the mass, and the speed is 6 meters per second. Okay, so that's easy enough. V squared, half mv squared. But now, what are all the forces acting on the particle that are doing work? That's the key. Okay, how many forces do we have in this problem? We've got three forces. Now, before you even look at the answer, which of these forces will do work, either positive or negative, or zero? Okay, so if this is moving in that direction, we know that the friction force will do negative work because cos of 180 is minus 1. Remember that the displacement, the velocity or the displacement is in that direction, delta S, and the force is in the opposite direction. So there's going to be negative work done by this force. What about this force, weight? Okay, well, only a component of that force that's acting in the same direction will do work, and it will be positive. This will have a component that does positive work, and the other component, which is perpendicular, will do zero work. What about the normal force? The normal force, because it's always perpendicular to the direction of motion, will do no work, zero work. Okay, so let's now look. So we're just going to focus then in terms of, in the second term here, we're going to focus only on friction force and the weight, but only the component of the weight. So let's look first at the weight, this weight and the work done by the weight. You agree with me that the weight is mg. That's what we have there, mass times gravity. Okay, but now we need this component. Okay, we need this component, and to get this component we would calculate it this way. It is S, it's the total distance, times sine of 10, okay, which gives us the vertical distance that it's traveled. Remember, even if it's going in this direction, you multiply the weight by only the vertical distance that it's traveled. So if it's traveled from there to there, the vertical distance is only that, that would be S sine 10. Okay? So there is our weight, the work of the weight. And then, what are we looking for? Here we're looking for minus the friction force, the kinetic friction force, which is mu k times n. Okay? That's what we're looking for. That's just the friction force times S. Don't make that mistake. Remember, it's force times the distance that's giving us the work done by this force. Okay, but we've got mu k, that is equal to 0.5, but we don't have the normal force, so we simply sum forces up in the normal direction, and we solve for it using this. Okay, there's my normal force. I plug that in to there, times it by my coefficient of kinetic friction, I get, there's my friction force, 8453.35. Remember, it's negative because it is opposing. It's going to do negative work because it's opposing the direction of motion, and we multiply it by S. So in this equation, and then on the right-hand side, if we're looking at T2 is half mv2 squared. So what is the final velocity? V2 is 0. So there's no kinetic energy on the right-hand side. T2 is 0, so that's why we have a 0 there. And we solve for our displacement, and it equals 5.76. Now look at this. They've just added a section in here. What if we had used chapter 13 techniques, the principle of force and acceleration? Okay, then you would have first carried out this equation, the sum of the forces in this direction, okay, is equal to mass times acceleration in this direction. Okay, we could have solved for our acceleration, and then only would we need to use this acceleration, because it's a constant, to then go use one of these kinematic equations to solve the displacement. So here we've done it effectively in 2 steps, 1, 2, whereas here we bypassed this step. We've bypassed it and we've solved it in 1 step using the principle of work and energy. Okay, so there's no problem in using either technique. It's just that in this case, using the principle of work and energy, we were able to bypass force and acceleration and go straight into the solution.